For this video, we'll be discussing the helium atom and obtaining approximate solutions using the various approximation methods that we discussed previously. So the helium atom is a system that has 2 electrons and a nucleus with the charge Z equals +2. The nucleus contains 2 protons and 2 neutrons typically, for helium-4 anyway. So we start off by enumerating what the particles are in our system. So we have a nucleus, and then we move on to sort of sketching and setting up our coordinate system. So we have a nucleus with a charge of +2, and we have an electron. We have 2 electrons. And they're each going to have their independent set of coordinates. And the distance between the nucleus and the nucleus and electron 1 is given by, we'll call that R1. And we have our electron 2. The distance between it and the nucleus is R2. And then we're also interested in the distance between the 2 electrons, and we'll call that R12. So these are the coordinates that we'll use initially to set up our forces, our potential energy, and develop a Hamiltonian. And then we will apply some approximations and come up with answers for what the total energy is for the helium atom. And it's worth reiterating the electron move independently of one another. And so each electron has its own set of x, y, and z coordinates, or r, theta, and phi coordinates. So in terms of motion, then, our kinetic energy is going to include the motion of both electrons. Right, if we want to talk about the total kinetic energy of the system, we have to talk about the total kinetic energy of both electrons, and that's going to be minus h bar squared over 2 times the mass of an electron times what we'll call del 1 squared plus del 2 squared. And so this represents from electron 1, and this one is electron 2. And so del 1 is if we have electron 1 has a set of coordinates x1, y1, and z1. Then del squared 1 is going to be given by d squared dx1 squared plus d squared dy1 squared plus d squared dz1 squared. Or similarly, the somewhat more complicated expression in terms of R1, theta 1, and phi 1. Of course, it's not going to be as simple as that. It has the various radial and angular components, and it's a more complicated expression, but it means the same thing as the Cartesian expression. And so we have those two terms for kinetic energy. What about the potential energy of this system? Well, there are the potential energy is dominated by these is determined by these electrostatic interactions between the three particles. And so there's an attractive potential term due to the interaction of electron 1 with the nucleus, and the same type of attractive potential, but with a different set of coordinates, x2, y2, and z2, for the electron 2 with the nucleus. And there's going to be electron-electron repulsion between electron 1 and electron 2. And that pretty much takes care of it, right? I don't think there's any other electrostatic interactions in the system. We've accounted for all the particles and how each particle interacts with the other particles in the system. And so then mathematically, in terms of these positions, the potential energy is going to be minus 1 over 4 pi epsilon naught z e squared over r1. So that's the attractive interaction between electron 1 and the nucleus, where z equals 2. And there's going to be an attractive interaction between the second electron and the nucleus, and then there's going to be this repulsive interaction between the two electrons. And so our overall Hamiltonian is the sum of kinetic energy and potential energy. And so it's going to be all that stuff added up together. The potential energy term and the kinetic energy terms. And we might be see, in the case of, say, the particle in a 2D or 3D box, or the harmonic oscillator, in a 2D or 3D box. And also for the rigid rotor, we were able to use separation of variables. So the kinetic energy terms are separable, right? You have del squared 1 plus del squared 2. However, the potential energy terms are not separable. And that's because of this R12, which we can think of R12 in terms of Cartesian coordinates is going to be x1 minus x2 squared minus y1 minus y minus y2 squared plus z1 minus z2 squared. And that can't be separated into a sum of two separate terms, right? They're sort of mixed in together underneath that square root sign, and they're squared and squared together, and or the differences are squared. So yeah, this we can't rewrite as a separable potential energy. So therefore, we can't write this in the form of we cannot write our overall Hamiltonian is equal to H1 plus H2. Now, we, of course, because this is all math and physics, and we can turn off temporarily, hypothetically, we can engage in counterfactual reasoning, at least for a time. We can't. We need to sort of flag the fact that we're dealing with counterfactual. When we're considering a counterfactual system, but if we turn off the electron-electron repulsion, hypothetically, then we have a separable Hamiltonian. Okay, and so we would have a simpler Hamiltonian that would, again, this is still hypothetical. We need to see if we can reintroduce. So we've gone into again into this counterfactual mode, but we'll see if we can reintroduce the electron-electron repulsion. So if we turn it off temporarily, then we have a separable Hamiltonian, and in fact, we can do this kind of somewhat separated Hamiltonian in that our Hamiltonian is equal to h for electron 1 plus h for electron 2 plus this additional term, e squared over 4 pi epsilon naught r12. Okay, so this is a almost separated Hamiltonian, and then if we just assume temporarily that that e squared over 4 pi epsilon naught r12 is not important, then we have a separated Hamiltonian. So we've kind of divided a Hamiltonian into the sort of pseudo-separable parts and then the unseparable part, the part that kind of mixes things together, mixes the coordinates together. So we can treat this e squared over 4 pi epsilon r12 as what we'll call a perturbation. And we won't worry too much about the details of what I mean by perturbation, but we could calculate an expectation value for the real Hamiltonian using our approximate wave functions. Okay, so this is like the variational method, but without a variational parameter. So our approximate energy, again, sort of taking our reasoning, borrowing from pieces of the variational method, except just not having the variational parameter part. We have our real Hamiltonian, again, which I've which is this Hamiltonian. And then we can do this for an approximate wave function, where these approximate wave functions would be solutions to the Hamiltonian, to the hypothetical separable Hamiltonian. In other words, this approximate Hamiltonian this approximate wave function is going to be a product of psi 1s, we'll call it psi 1s1, psi 1s2. So this would be the wave function would be the wave function solution for H1. So that would be for a single electron around a helium nucleus. So this would be the H atom type solution for the Z equals 2 helium nucleus. And that would be and then you would put the coordinates on it, which would be x1, y1, and z1, and then you would have a product of that and the wave function that corresponds to the solution for H2, which would have the coordinates x2, y2, and z2, or r2, theta 2, and phi 2. And so we're going to sort of use this approximate wave function. Again, so far what we're doing is consistent with the variational approach. We just haven't introduced a variational parameter yet. So we're dealing with this in sort of stages. So first we're dealing with setting up, we have this approximate wave function solution. That's definitely part of the variational approach. And it's a wave function that's based on a a simpler system where we've turned off this electron-electron repulsion. And then we're including this electron repulsion in this approximate Hamiltonian, and in the real Hamiltonian, calculating the expectation value for the approximate wave function. So our approximate energy, again, we're taking these approximate wave functions and using the real Hamiltonian or the full Hamiltonian. So that's, and of course, so we can't actually solve the eigenvalue problem of the Schrodinger equation because these are not eigenfunctions of the real Hamiltonian. They're eigenfunctions of a simpler Hamiltonian. But we can calculate the expectation value. So we have this psi1s1 star. We're going to make this operator sandwich, right? When we're going to sandwich this real Hamiltonian in between the approximate wave function and its complex conjugate. And we're using 1s parentheses 1 to say this is a hydrogen 1s wave function, hydrogen-like 1s wave function for z equals 2, so for the helium nucleus, and then the parentheses 1 indicates that it's r1, theta 1, and phi 1, or x1. That's the parentheses is telling us what our coordinates are. This is going to be d tau, and of course this is an integral over all space. And in this case, this would be an integral over 6 coordinates. Right, r1 theta 1 phi 1, r2 theta 2 phi 2, etc. And if we consider our H real, then expand, we get that the H real acting on if we plug this in, and I'm going to skip these steps, but I believe in the typeset notes and or something you can do on your own is to sort of work through how when you apply this, you end up with the following results. So you're going to get E1, which would be, again, the energy of associated with electron 1, assuming that there's no electron 2, right? So assuming that, or at least that it's not interacting with it. And then, of course, there's going to be an energy associated with electron 2. And then there's going to be this integral, this leftover part, which is going to be an integral of psi1s1 psi1s1, psi star 1s1, psi star 1s2, e squared over 4 pi epsilon naught r12, psi 1s1. Okay, so this is an integral that is somewhat complicated, but nevertheless, you can either calculate it out numerically, and I believe there's actually an analytical functional form for this integral. We're not going to necessarily worry too much about that, and we'll skip along, and because again, there's a lot. This is just sort of our first step. I don't want to spend too much time on it. We'll come back and use a variational approach shortly. But if we add all this together, we get that our approximate energy. Now, if we just include E1 and E2, we end up with something that's like minus 100 something electron volts. Let me see, I've got the numbers here. Minus 108.8 electron volts. But then there's the integral here, that's going to give us a positive value for energy, right? Everything there has a positive sign, and that gives us, oh, I don't have the number for that, but when we add all of those together, we get equals minus 74.8. So yeah, more than 30 electron volts in the positive direction. Yeah, you can do the arithmetic, but we end up with minus 74.8 electron volts. An electron volt is one of these energy units that's often used in atomic physics. It's very convenient because it's the energy of, if you take a single electron and accelerate it through a voltage difference of 1 volt, then it gives you a certain amount of energy. And it's a convenient unit for a lot of atomic spectroscopy, particularly for photoelectron spectroscopy, where you might determine the energy of electrons in say a photoemission experiment by using a retarding potential bias between two plates. So anyway, so that gives you our approximate energy of minus 74.8. The actual experimental value, or from a higher order calculation, is minus 79.0 electron volts. And so this is an error of 4.2 electron volts, or about a 5% error. And so for an approximate method, it's not too bad. We haven't even introduced a variational parameter. However, if we completely ignore electron-electron repulsion, so omit that integral over the electron-electron repulsion potential, then you end up with minus 108.8 electron volts, which would be a whopping error of say 45%. Right, so we've gone from a 45% error if we completely ignore electron-electron repulsion, versus if we include it in this very approximate way, using this not quite variational method, then we end up with about a 5% error. And an interesting side note, this approach, the math, the derivation of it, or the sort of theory behind it is a little different, but in terms of the integrals involved, This is a first order perturbation theory. First order perturbation theory result, because essentially what we've done is we've divided up our Hamiltonian. So we say we've got our perturbed Hamiltonian, which we'll call H1. That's going to be equal to some approximate Hamiltonian H0 plus a perturbation potential. And so this maps onto how we've described our problem so far, in that H0, that's just the individual Hamiltonia of each electron interacting independently without the other electron. With no electron-electron repulsion, interacting with the helium nucleus. And then we've tacked on the perturbation, which is in this case, is the electron-electron repulsion term. And the perturbation theory result is that the first order perturbation energy is equal to the zero order energy plus the expectation value of the perturbation potential, and that's evaluated for the zero order wave function, which in this case the zero order wave function are just the hydrogen-like 1s wave functions for the helium atom. Okay, anyway, so that's all we're really going to say about perturbation theory for now. There's a matrix approach, which we will hopefully have a chance to talk about later in the course. But this is a reasonable introduction to perturbation theory, although we're treating it more or less as an aside here. Okay, so now let's, for the next lecture, actually, I think that's enough for this lecture. For the next lecture, we'll see if we can do a little bit better than this by introducing a variational parameter.